We will be hosting Professor Yan from Xi'an Jiaotong University. Professor Yan is the director of the International Machinery Center at Xi'an Jiaotong University and is well known in the area of intelligent industrial fault diagnosis. So today, he will be delivering a seminar on physics-informed deep learning for intelligent fault diagnosis. Professor Yan's IEEE Fellow, ASME Fellow, and is a chief editor of IEEE Transactions for Instrumentation and Measurement. So we welcome collaborations and discussions after the seminar. Welcome, Professor Yan.
Thank you, Dr. Dunn's introduction. I think thank you, Lahore University, to invite me to be here. Today, I will talk about something on physics-informed deep learning for intelligent fault diagnosis. Before my talk, I think I would like to introduce a little bit about our city and our university. Our Xi'an Jiaotong University actually located in Xi'an, the central China, and actually Xi'an is a historic capital of Shanxi province, and it's also an ancient city. So it has 13 dynasties that established capital in Xi'an. Also, you know the famous Silk Road. Xi'an is actually the starting point of the Silk Road. So from Xi'an to all of the world. So as you can see here, the Terracotta Army is very famous. Also nowadays we have a very light show in the area. It's called Grand Tent Mall. So during night, people can just walk through the whole street. So the building was built mimic the ancient city. So actually, our Xi'an Jiaotong University originated from Nanyang College back in 1896. Then later on, we changed to Jiaotong University. But after 60 years later, so the Jiaotong University moved from Shanghai, actually moved to Xi'an. Now we have actually in 2016, we have this 120 anniversary celebrations. Several days later, we moved to a new campus. We call it the Innovation Harbor of Western China. So this is the landscape of our new campus. So our School of Mechanical Engineering is the first one moved to this new campus. So when we moved to this new campus, all of our graduate students are moved there. So actually our undergraduates are still in the main campus in the city. So we, in this new campus, we don't call us as the School of Mechanical Engineering. So we have the name as IAS Academy of Frontier Equipment. So actually the faculty members are all the same as the School of Mechanical Engineering, but we are more focused on research in this new campus. So altogether, we have one international machinery center, which I'm working on there, and plus 9 institutes. So something about air engines or aerospace manufacturing, robotics, and also design, and also advanced manufacturing and precision engineering. And also, there is our strength is about the intelligent diagnostics control for equipments. Nowadays, we also have the new institute for new energy. So here is this new buildings. Actually, the whole building is about 180,000 square meters for the workspace. So for our Academy of Frontier equipment, we occupy half of this. So which means we have 90,000 square meters for research. So here is our team members working in our international machinery centers. Actually, most of them are from abroad. They went abroad to get their PhD degree. Then after several years later, we recruit them back to China to work. So as you can see here, actually, there are quite a number of young faculty members graduated from UK. So now we are also welcome talented people from all around the world to join us. We have actually a very good this workspace, as you can see in the right side. So back to my today's talk. I will briefly introduce some background and then talk about this explainable artificial intelligence. Then I will talk about this physics-informed data science, how we can integrate physics models with data to do intelligent fault diagnosis. We'll give you a case study to show how physics constrained neural network can be used to assess the gear pump wear. It's a kind of failure because our sales failure. So then I will give some conclusions and some future directions. I think maybe it's more interesting to explore. So as we know, I'm in mechanical engineering. So nowadays, actually, manufacturing actually plays an important role in this world's leading economies. So there are some losses due to maintenance issues. This kind of losses are actually proportional to the size of manufacturing industry. So they can create some negative impact on this world economy or worker safety and the well-being. So then when we talk about intelligent fault diagnosis, actually it belongs to this whole spectrum of this intelligent maintenance, right? So what is actually intelligent maintenance? So from the video, the definition is an intelligent maintenance system. Actually, it's a system that utilizes collected data from machinery in order to predict and prevent potential failures. So actually, intelligent maintenance involves lots of things. For example, this you have basic systems, right? You need to get data. Right? Involve some maybe sensing techniques. Then when you get data, you need to analyze data, do prognosis diagnosis and prognosis. Based on these results, you need to do some root cause analysis, and also, for example, for this remaining useful life prediction. So based on this, your prediction results, you may need to do some maintenance optimization. So this is intelligent maintenance involve all of these research activities. So with this kind of intelligent maintenance, so manufacturers expect to maybe reduce the downtime, eliminate these machine failures, or reduce this capital investment or sometimes reduce this maintenance cost, right, by a certain number of percentage. This is when we do this intelligent maintenance, it can bring this kind of benefits. So there are some key questions I think Professor Jackson talked about yesterday. That is 4 different parts. So the first one is condition monitoring. What we want to do is we want to use the data to describe this machine performance. So we need to do condition monitoring. Then we need to do diagnosis. So we want to know what is the root cause for this machine failures. And also we want to know how this machine performance deteriorate with the time, right? So we need to do some remaining useful life prediction. Also, so after we get this predicted results, we want to know what is the optimal operation condition that can maximize this service life. That is kind of operation optimization. So all of these 4 issues are related to this intelligent maintenance. So back to 2016, this CRP one review papers. So point out that currently there is the kind of integration need for this high-end equipments for the manufacture and service. When we talk about manufacturing, it's about you design a product and then make that. Then the service means what? After the product is produced, you need to be in some use, right? Then it's in its so-called operation and maintenance stage. So this kind of integration can bring some benefits. So, for example, this kind of intelligent maintenance can help upgrade and improve the design and manufacture of those high-end equipments. Here we talk about high-end equipment means, as you can see here in this thing is about these L engines, right? Nuclear power plants, helicopters, high-speed trains, and wind turbines, right? Because those equipments are designed for being using a long time, maybe 30 years, 50 years, not like our desktop, right, or smartphones. So everyone use smartphone every year, maybe a new generation smartphone is released, the people just get a new one. So the older one are still in very good conditions. So for this high-end equipments, so once it's being used, it will last maybe 30 or 50 years. So most of the time actually is in service. So we need to do condition monitoring and for diagnosis this type of things. So here give you 2 examples. United States, the GE, they have this they utilize their predicts platform to monitor 5,000 engine performance data in 1 million past operation and maintenance data to establish a so-called manufacturing service closed loop feedback systems. So within this closed loop system, they can help to make or design their next generation engines. Also, I think in our UK, the British, that Rolls-Royce, they have this kind of gas turbine manufacturing service integration. They build this intelligent ship system. Within this system also has this kind of functionality of diagnosis, operation and class optimization, and this type of things to realize gas turbine manufacturing service closed loop. So then they can upgrade their new generation of gas turbines. So from the life cycle point of view, so we consider this high-end equipment conclude consists of three parts: design and manufacture, service and monitoring, and operation and maintenance. So with each stage, there will generate lots of data. For example, for the design method, you have you need to design, right? You have many the design data, right? Also, when you produce your product, you have many quality data. What I was thinking, if we can utilize those design data and quality data to help us to better do this monitoring and this operation and maintenance. Because normally people are never use this kind of design and manufacture data to do to help this monitoring task. Also, from this service and market and operation and maintenance data, there are many monitoring data, performance data. Also, there are some failure statistic data. So we are thinking if we can utilize this kind of data to help us to improve our design. So we want to actually integrate this all of this life cycle data. So we build this kind of digital thread systems. We use this design knowledge to provide a feed-forward knowledge to help condition monitoring of diagnosis. And also we utilize this operation and maintenance knowledge we extract from this monitoring data, then to provide some feedback to help they improve their designs. So how we can do this kind of integration, then what we're trying to do is we based on this intelligent operation and maintenance knowledge we extract, then to help to do this design improvement. So over the past years, we have built up this kind of technical roadmap, also from this life cycle point of view. So including the three stage, you know, in this design and manufacture stage. So you can based on this users requirement, right? You can build some kind of digital models to do some design, and then manufacture, produce your equipment. And then after that, so this equipment are being used, so they will generate lots of monitoring data. So you can source, for example, big data mining, right? You can do some kind of knowledge discovery work. So also, so with this kind of knowledge discovery, you can do diagnosis and prognosis. So based on this diagnosis and prognosis results, you can do many things for this operation minutes. For example, you can help to do this spot part management, to do some inventory management, also do some, for example, spot part planning, this kind of work. So the most important thing is you can do some you can identify some fault source. So when you identify this fault source, you know which part of your equipment is easy to be damaged, right? Then maybe that's because when you start design, you didn't think about that part. For example, okay, maybe some part has high stress, something like that. So it's all. So when people design the product, they didn't consider that. So, but from our diagnosis and prognosis results, we identify some weak parts. Then with this knowledge, we can provide some kind of feedback to this designer or to manufacturing factory, help them to improve their next generation of products. So here, diagnosis and prognosis plays an important role within this life cycle management of high-end equipment. So actually, it belongs to a predictive maintenance. So the predictive maintenance is rated by the CV Insight as one of the trends of artificial intelligence in 2019. So nowadays, people are using artificial intelligence to do this diagnosis and prognosis work. So here shows just an example how traditional for diagnosis be implemented. You have sensors, you get data, right? You do some signal processing, for example, spectral analysis statistics. You get some, for example, threshold. So based on this state index and you set a threshold, you can evaluate, okay, if this system you are monitoring has some problem. And nowadays, for this modern intelligent method, so the sensors become smart, right? Sensors can not only get a sensor itself, it can also do some, for example, signal processing task. Also, we can use some HAI type of things to do a data acquisition. Then for this data analysis, you can use some learning algorithms. That's why nowadays deep learning transforming this method more and more popular in for diagnosis area. And then based on your learning algorithms outputs, you can do some evaluation, okay, to evaluate if your monitoring system or monitoring machines has some problem or not. So deep learning, as you know, so actually Hinton, right, he published the deep learning paper in Science back to 26, right? And then later on, the Nature also reviewed this deep learning as one of these 6 breakthrough technologies in this emerging science and technology trends from 2016 to 2045. Also calling on that deep learning will be the core technology for this data analytics in the future. So we did a little survey on how deep learning has been used for diagnosis. As you can see here, we did this research in viral science. As you can see here, so these publications so increasing so quick like, over the years. So if we look at some sub domains, for example, the network structures or transfer learning or supervised or unsupervised, this type of things, or explainable artificial intelligence. Also, for each of subdomains, the publications are also increasing. So, but when we specifically take a look at this explainable artificial intelligence enabled for diagnosis, it still occupies a really small part in this research of our PHM for diagnosis this area. But from this spending, you can see this explainable artificial intelligence for diagnosis continues to grow. So nowadays, so it looks like this kind of explainable artificial intelligence for diagnosis has become a very hot research area. So then what is exactly this explainable artificial intelligence? So from a psychological point of view, the explainability is about humans' understanding of decisions. So from the left side is our traditional deep learning models. So this kind of model cannot tell you why you get this kind of decision, give input. But with the right side is explainable artificial intelligence models. So with this model, it can tell you why you get this output. So it gives you a trust. So in our for diagnosis area, is it necessary to use this explainable artificial intelligence techniques? So we know. So these applications, so previously for this NLP or recommendation systems, they are performance driven, but for our industry application or for the healthcare applications, they are this so-called the safety first, right? So they are more care about safety. If your model give you a wrong decisions, then it means it can not be reversed. So traditional deep learning models is a black box model. It cannot tell you why this kind of decision be made. So with this kind of results, our human being only have two choices, either believe or not, right? So during this kind of decision-making process, because our human being are not being involved in this decision process, so people are hesitant to use this kind of black box models, especially in industry. So that's why we need explainable artificial intelligence techniques to be used for machine for diagnosis. So then how to implement this explainable deep learning? So actually we know this deep learning model is a kind of end-to-end process, right? So we can realize or implement this explainable artificial intelligence through different approach. But first is from the data point of view. As you know, if you can get a complete set of data, which means all the conditions you already know, then the model you build must be explained. Because given any input, you already seen it. So the output must be trusted. Or you can build some kind of explainable models or some new learning algorithms to realize explainability. We call this explainable model and a new learning approach as an ad hoc approach. So you can use design some interpretable models, or you can use some regularization techniques to actively change the models. So that can affect your model performance. Also, sometimes once you already build a model, you may need use some kind of post hoc techniques to explain why your model give such kind of results. For example, you can use some visualization techniques. You can use some sensitivity analysis techniques to explain your model outputs. So it's kind of a post hoc approach, which can only help you to explain or train a model, but will not affect your model performance. So over past years, we have done some research work, both from head hoc approach or post hoc approach. For example, we can embed some domain knowledge to our local model designs, or we can use some kind of global model design techniques. For example, use unroll optimization algorithms to notable neural networks. So also we can using some regularization methods that can induce some physics information into optimization of neural networks. So, for example, this so-called physics informed loss functions to get interpretable representations. We can also analyze, for example, these latent features within network structures to find out the dominant ones that you can do some visualization techniques to explain your structure models. So in my today's talk, I mainly talk about how we can embed this physics-informed laws to deep learning models to help us get explainable deep learning models for diagnosis purpose. So before the rise of deep learning technologies, so in order to get some evolution laws from basic systems, so our observation methods undergoes a series of change. For example, from this experiment induction and to model deduction, and then to the simulation and this calculation. Nowadays, we are entering into the data science age, right? So as you know, with the change of this observation method, so we have less and less physics and more data, right? So actually, our engineering applications indicates not all of the problems can be solved by only the data. So we need, we must think if we can integrate the physics knowledge with data to do a better job. So we know the purpose of modeling is to mine the evolution law from data or from a phenomenon, right? There are two different approaches. One is the inverse paradigm that's based on this data type. Other one is a forward paradigm is based on base models. So for each of these approaches, there are pros and cons. For example, for this inverse data science-based method that is relying on this association rules, right, to mine some kind of loss from the data, right? It has this adaptivity to high-dimensional data, but it's kind of black box model. It has a weak interpretability. But for these business models, it relies on the causality to based on some, for example, physical laws, right? You can build your physical models. It's a black box. It's a white box model. It has a strong interpretability, but as you know, because nowadays the equipment now becomes more and more complex, so it's hard to build an accurate physical models. So what we are trying to do, we try to utilize both advantages of this data science and physical models, try to integrate them, then present a so-called physics-informed data science approach to help us to do a better for diagnosis work. So basically, there are three strategies to implement this physics-informed data science from a data problem or inductive problem and learning problem. So from the data problem, as I said before, if you have a complete data set, then deep learning can give you a very accurate performance, right? So for this inductive problem, so actually you can induce some general laws from observations of multiple individuals, right? For example, you can maybe try to find some symmetry properties of your observation systems, these kind of things. And also for this learning problem, actually it deduce some specific models for individuals, starting from this first principles. So in our engineering domain, if we want to implement these three strategies, so for how we do it, so for data problem, so we can actually build up a piece with the data augmentation techniques, right? So that's why nowadays the digital twin, everyone use digital twin, right? If you can actually build a digital model of your actual physical systems, you can utilize your digital model to help you generate data, right? Then it will help you train your deep learning models. So for industrial prep, actually, you can build up a physics-informed neural architectures, right? So you can force your outputs that conforms physics intuitions. For this learning approach, actually, it's a kind of a deductive approach, right? You can build some physics constraint loss functions to help you guide your network optimization. So here, I will show you a case study how we use these physics constraint loss functions, embedded this function into our models to do a for diagnosis task. So the case study is about we build up a physics constraint variational neural network for this state assessment of a gear pump. So because my host is aeronautics department, so I show you an example. So we know the air engines, right? It's very important for airplanes, right? So the air engine fuel control units actually is when it's working, it's under very strong vibration, high pressure, and high rotational speed, right? This kind of fuel control system is key systems which affect the safety of this air engine operations. So based on a study by this American Institute of Aeronautics and Astronautics, so they gather statistics between 1986 and 24 about 387 fuel system failures. So among these 383 fuel system failures, 66 are directly caused by fuel pump failures. 54 are hydraulic line failures, but which are still mainly caused by fuel pump failures, which means this failure rate of fuel pump in the fuel system failure is as high as around 31%. That's why I want to show a case study. We are focused on this fuel pumps. So there are two major fuel pumps. One is the gear pump, another is the extra pumps. So in today's case study, I will show how we do this well assessment for a gear pump. So we need to build up the fixed models of this gear pump, right? So based on our study, actually this end phase wear is the main cause of the failure about this gear pump, and also this end phase wear fault mainly occurs on the surface of these blocks. So if we want to monitor this, or if we want to diagnose this failure of gear pump, we need to know, okay, what kind of signals can we get, can indicate the failure of gear pump. So we are trying to find a mapping relationship between the interface where the output signals. So we know when the interface wear happens in this gear pump, it will cause this variation of natural clearance there. And this variation will cause change of boundary condition about the flow field in the gear pump. So as a result, it will cause a variation of its outlet pressure transition. So which means if we want to monitor this gear pump, we can measure these pressure transitions, right? So we can analyze that pressure transition signals and to diagnose if that gear pump has some problem. It has a direct relationship. So then how we can induce the learning curve in neural network? So we actually start from the first principle. We can build some formulas to understand the physics world of the here physics world is the gear pump, right? Then embed it into a data-driven learning process. So here, providing you an overview of our proposed physics constraint variation and neural network. Actually, we built up our response model of that gear pump. Then we embedded that response model into our physics generation models to get some or extract some features that can characterize the physics of that gear pump. Then we also use some inference neural network to do our diagnosis purpose. So I will show some details how we implement this. So we first build up our physics models. We utilize the fluid analysis to derive the physics models. Actually, it's the governing equations and MS equations, right? Normally, it's hard to solve mathematically. So we use some special method. We do some special discretization. Then we get these pressure compensation models as shown in the lower right. It actually contains some amplitude modulation and also the frequency modulation, right? So it has some spectral coherence and some wavelength noise. It's actually a mix of this multi-scale vortex. Then we can build some physics laws here. Actually, all of the parameters are derived from this pressure compensation models. So we build up this kind of in the upright, this kind of network structure. Actually, the observation signals, right? So go to this inference network, we can extract some physics features. We utilize these physics generated models that based on our response model, right? To reconstruct signal. If we can perfectly reconstruct the signal, which means that physics features you extract and characterize the gear pump status. So then we can, based on those physics features, extract from these deep learning models. So we can do, for example, this degradation assessment, or we even can do evaluate if that system is has some uncertainty. So that is the approach how we embedded these physics models into this neural network. So then we do experimental study. We set up this test bench and we do some data pre-processing. We try to remove some unstable rotation speed influence, unstable pressure influence. So we set up some parameter settings for our so-called physics constrained neural network structures. So here shows the results. So the left column is our proposed research proposal approach. Others are some traditional, for example, MRP plus open code, RISLET, LSTM, LET. As you can see here, our proposed physics constrained variational neural network can clearly identify with the where increase. So it has a increasing trend for that some merit. For example, the distance merits or similarity merits. But for other approach, traditional approach, the some maybe has some trend, but others you cannot find this trend with the increase of weight. So we can also take a look at this reconstruct the signals, use different approach. As you can see here, so the upper right is our approach reconstruct signals. The lower right is traditional reset encoders. So you can see with our proposed approach, you can use a few similar coefficients to reconstruct. If we take a look at from the frequency point of view. But if you use traditional method, you need more frequency components to reconstruct the original signals. That's one of the advantage because we embed our basic knowledge in our network structures. So we can also take a look at some systems uncertainty. So actually, those basic features we extract only some of the features as a dominant for that systems, but others are just very small numbers, which means that those features are not affect the systems significantly. So if we from the TSNE visualization point of view can see, because of this physics constraint, the control trajectory has a very controlled trajectory because we added the physics constraints on that models. For others, it's just a random. So we can also interpret the extract basic features from this energy distribution point of view. So the left side figure is our actually the extract basic features. The right side is just the traditional Fourier transform of this position signal. As you can see that it has a consistent structure of energy distribution with your with our this Fourier transform results. So actually, it reaches maximum incremental frequency of your gear pump, and then goes down. So this extract physics models, physical features from these deep learning models and well matches this signal itself, its energy distributions. So in summary, in my today's talk, I introduced a physics constraint data-driven models for this well state assessment. I gave experimental feature learning methods based on physics constrained variable neural network, where these learned features actually can represent the energy distribution. It has explicit physics meanings, so we can even can estimate the system's uncertainty. From the life cycle management point of view, as I showed in my talk, the background part. So actually, this diagnosis results and provide some feedback for the design, right? So the physics-based model help in gain some knowledge. We know the system's uncertainty related to this network clearance, right? So actually, because so the clearance changes, it will affect your system's uncertainty. Then maybe during your design stage, you can set up a proper clearance value to make your system more stable. That we can get this kind of logic from your diagnosis results to help you set up some kind of clearance values. So in conclusion, I just talk about AI enabled this intelligent diagnosis approach So one case study shows the power of AI-enabled diagnostic method. So it also provides a collaborative perspective for data science and physics models for diagnostics by leveraging this physics-informed deep learnings. So for future directions, we think how to balance physics and data, right? It's very difficult because when you train your models, we know you add some constraints, then training will become difficult, right? So how we can balance this? Also, if we can model the physics knowledge for more efficient collaboration between physics and data science, right? Also, if we can automate some feedback of design for online optimization. And the most important thing is if we can break through some physics problem for some new knowledge discovery. That's why all knowledge, the AI for science is very popular. Right? You can use AI, maybe find some physical equations. That's the science people are doing now. So I would like to acknowledge my collaborator, also the National Science Foundation of China support our research. So I would like to conclude my talk. Thank you.